So the first part is the chemistry of acids and bases. Well, actually, if you notice, the packet is a lot thicker than the other one. We'll be in this one a little bit longer than we will the other one. So this unit is basically going to be acids, bases, buffers, and Ka and Kb, or acid-base equilibrium. When we're talking about acid-base equilibrium, we will be talking about weak acids and weak bases. If it's strong, it's 100% dissociation, so it's going to be just your straight-up pH calculations like we did in Chem 1. They're all back there. Will you pick them up for them? Okay. Okay. So let's start with the beginning. An acid comes from the Latin word meaning sour, like lemons are sour. Anybody? You should. I mean, it's just some little background information. Alkali is from an Arabic word meaning from the ashes, because when you burn things, they make a base. They are very slippery or bitter. Anybody accidentally taste soap when you were little, thinking, "Oh, it smells good. It tastes good." Doesn't. Okay. Okay. They're very important in your everyday applications. Okay, so acids and bases are extremely important. That's why we're going to study them. It's the third to the last unit. After this, we only have 2 more units, which is thermodynamics and electrochemistry. But this is a longer than average unit because it is important and it shows up a lot on the AP exam.
So is it like alkali metals, or is it like another word for base?
Another word for base. But the reason the alkali metals are called alkali metals is when you react them with water, they form bases. So like when I put sodium in water, it forms sodium hydroxide. And so that's why they're called alkali metals. Same thing with the group 2, alkaline metals also make bases in water. Okay. There are 3 definitions of acids that you need to be aware of. One's going to be more important than the other 3, but you do need to be aware. The Arrhenius definition, and this is Chem 1 stuff, so hopefully it kind of rings a bell. The Arrhenius is going to be your strictest definition, meaning there's going to be less things that are considered an acid under this definition. Their definition of an acid is that it donates a hydrogen in water, and their definition of a base is that it donates a hydroxide. Okay. The ammonia isn't a major exception because ammonia actually doesn't have OH in it, and so this is one of the strictest definitions. We don't use it a lot, other than know that the proton donates a hydroxide.
Isn't the correct one the electron pair one?
No, we're talking 3 different definitions depending on what we're doing. There's 3 definitions. There's not one more correct. It's just what you're looking at. I'm recording, so let me. Okay. So the Bronsted-Lowry definition is going to be the most common definition that we'll use, and it's going to be the one that we deal with the most. So this is the most common, and it's the one that says that the acid donates the proton and the base accepts the proton. This theory is better. It explains ammonia as a base, which we clearly know that it is, and it's the main theory that we're going to use for our acid-base discussion. The third theory is the Lewis definition, and it is the broadest definition, meaning there will be more things that are considered an acid or a base under this, but it's usually pretty much just used in organic chemistry, and that's the one that's the electron pair, donor, and acceptor. Okay. In the AP exam, they don't even really test Lewis acids and bases. They might need you to know the definition. Whenever we talk about coordination compounds, that can also be, but in terms of what we're doing for this unit, we won't refer to it again. We're going to be doing pretty much exclusively the Bronsted-Lowry. So the Bronsted-Lowry, if you remember from Chem 1, is the one where we have conjugates. You have a conjugate acid and a conjugate base. Okay, so an acid has a conjugate base. It's basically what's left over after the acid donates its hydrogen. And then the conjugate acid of a base is what's left over after a base accepts a hydrogen. And so here we have some examples of your acid becoming your base and your conjugate base. So here we have these would go together and these would go together. Okay, acid goes with the conjugate base and then these go together. Do y'all remember that from Chem 1? Okay, and then here's your acid, there's your conjugate base, and then here you go. Okay. So hopefully that rings a bell, and I don't need to go over that too extensively. But they are going to differ by the presence of one hydrogen unit. So today's a lot of refreshing from last year. Okay. So in each of these examples, notice we're forming the H3O plus. That was for the acid base, but sometimes you're going to be forming the hydroxide. Okay, so here we have the base being NH3, so its conjugate acid is NH4 plus. The acid was water, and so the conjugate base is OH minus. So this time we're noticing the formation of the OHs. Okay, the OH is called hydroxide. Of course, we should know that by this point in our life. The H3O plus is called the hydronium. Okay, and it lets you know that the solution is acidic. If you see the hydroxide, then it's going to be basic. Okay, so let's identify here. So HBr is what? The acid or the base? HBr? So that makes NH3 the base. So what is the conjugate base of HBr? Br minus is the conjugate, and then NH4 is going to be the conjugate acid of ammonia. So what is the conjugate base of H2S? HS minus. And then the conjugate acid of NO3 minus? HNO3. Yeah. Because if it's a conjugate acid, they're telling you that this is a base. And what is the base's job? To accept the proton. Yeah. So it's going to be HNO3. All right. Acids will only donate one proton at a time. We didn't really talk about that in Chem 1. If we had H2SO4, we just assumed it all went away at one time, the hydrogen. But actually, they donate one proton at a time, which is going to be part of our problems later on that we do because, for instance, H2SO4, which is sulfuric acid, is a strong acid. Once it donates one of its protons, it becomes HSO4, which is no longer a strong acid. It's a weak acid. So that's where our equilibrium will come into play. If you have a monoprotic acid, mono means one. It has one proton to donate. Diprotic is two, so like H2SO4 or this oxalic acid they're showing here. And of course, polyprotic is having more than that, which is usually three in case of H3PO4. You can have polyprotic bases as well because they can accept more than one hydrogen, but again, they're doing so one at a time. Okay. So the PO3 right here would be polyprotic because how many total hydrogens could it accept? Three. So it's polyprotic base, but it would accept one at a time. You can't give it all three at once. Okay. You typically see these terms more than polyprotic bases, but you do need to be aware of that you can call them that. Yes.
So are like your strong acids the ones that can donate more than one hydrogen, and your strong bases are the ones that can receive more than one?
No, that's not a measure of strength because your halogenic acids, with the exception of HF, are all strong, and H2SO4 is also strong. It just so happens that it has two. Has to do with their bonding that makes them strong, because we're fixing to get into definitions of what makes something strong. Okay. There's amphiprotic or amphoteric, whichever way you want to say it, is molecules or ions that can either act as an acid or a base. Okay. Water is the biggest example of something that's amphoteric because it can act as an acid by donating, and then it becomes an OH on the other side, or it can act as a base by accepting, and then becomes the hydronium, H3O+. There are other things that are amphoteric. For instance, whenever I dissociate H2SO4, remember I said it does one proton at a time? So now it leaves behind this HSO4 minus. This substance would be considered amphoteric because it could accept a hydrogen and go back towards H2SO4, or it could give away another hydrogen and become SO4 minus. So that substance would be amphoteric because it could act at that point as an acid or a base depending on what solution it was in. Yes? You have a question? Oh, thought you were raising your hand. There's other examples, but water's the most common example, not the most example. That makes no sense. So here I want you to write the dissociation or the ionization of each of these acids, omitting water, because when we're dissociating things, we are assuming that it's in water, because if it's not in water, it won't dissociate. Same thing when we do dissociation of ionic compounds, where the water is assumed to be there. Okay, so take a second to do that. Okay, so I did those first three. Does that look right to y'all? So what y'all did? Okay, so you're just going to break them apart and take off a hydrogen. So talking about relative strengths of acids and bases, that was Jared's question. What makes something a strong acid or a strong base is the ability to completely dissociate in water. So it's 100% dissociation. And they have very large dissociation, or they have very large K values, so we don't actually we don't even report their K values because it's 100%. Yes?
So that just means that they're going to get rid of all their hydrogens or take in all the hydrogens?
So that means when I dissolve them in water, they're going to 100% break up to hydrogen and chlorine. For instance, HCl is a strong acid, whereas acetic acid is not a strong acid. So in acetic acid, I would get some hydrogen and some acetate, but largely I would have mostly acetic acid still bonded together. Okay. Same thing with bases. So if it's a strong base, say for like sodium hydroxide, it's going to 100% break up to sodium and hydroxide. But if I had a weak one, say beryllium hydroxide is actually a weak base, then I would have some beryllium and hydroxide stuck together. Or ammonia is a weak base. So I would get some dissociation, but for the most part, then NH3 is going to be still stuck together in water, okay? Which is going to be a big portion of this unit of calculating pH for those weak acids and weak bases, and also calculating the percent dissociation. So that's going to be the strong acid, strong base is a very small portion of this unit, because the calculations are straightforward, because if it's a strong acid or a strong base, we'll find in a minute that we can just take the pH of the concentration and get it. But we can't do that with the weak, okay? So here's another thing that's going to be important right here, and that is do not confuse concentration with strength. And just because we say something is a weak acid doesn't mean that it can't hurt you, okay? For instance, hydrofluoric acid is considered to be a weak acid, but it will still hurt you very greatly if you get it on your skin. It has a nasty habit of wanting to combine with calcium, so when you get it on you, it likes to keep just going until it gets to your bones, okay? And if you've watched Breaking Bad, which I do not watch that show, nor do I condone it, but that's how he gets rid of some bodies.
Wait, isn't that because fluorine is so strongly bonded?
We're going to talk about that in a second as well. It's going to be on the next one, okay? Strong acids, you just basically have to memorize the six, the big six. HCl, HBr, HI, nitric, sulfuric, and perchloric acid, okay? Memorize them. No way around that. Memorize them, okay? And the reason that HF is missing is because in your HF, you've got a very strong bond between the H and the F, and so it doesn't break apart. So the strong bond makes it a weak acid because it does not want to break apart. And that's because of the relatively small size of fluorine and hydrogen. Their nuclei are very, very close to each other while they're sharing that electron, so it's harder to break those apart. Also recall that fluorine is the most electronegative, so it's hanging on for dear life, so to speak. So that's why HF is left out of the strong halogenic acids. Yes?
So these are like the only strong acids and all the rest are weak?
Yep. There's basically only 6 strong acids and the rest are weak. So 6 things are not hard to memorize, are they? Huh? Some view it as there are some schools that say it is, and there's some schools that say it's not. For the most part, we say it's not, but if it was to show up, you know, the chemistry is always changing. They always come up with things that, you know, oh, well, we decided it is, you know. But HF for sure is not one, because it's the strength of the bond between H and the F. It doesn't exist. I mean, it exists, but there's not an acid with it. It's such a rare amount. When you're talking about within a group, let's say like the chlorates, the more oxygen present in the polyatomic of the oxyacid, the stronger it is within that group. Okay, that's a trend, but not an explanation. Remember, we don't explain things with trends. That's just to kind of help you know it. You have to explain it with words. Okay. First of all, you have the acid is bound to the oxygen and not any other non-metal part. Oxygen, of course, is very electronegative and attracts the OH bond towards itself. If you add more oxygen, the effect is magnified, and there's an increasing electron density, so it makes it stronger for more dissociation, easier to break apart. Okay? So more oxygens. That's why HClO4 is stronger than HClO3. That's why H2SO4 is stronger. It's a strong acid, whereas H2SO3, sulfurous, is a weak acid. Okay, here's a pictorial of that in your relative Ka values. You can see how it goes down, especially right here. Here's our higher ones. Here's our higher ones. Oops, wrong one. I circled the wrong one. And then that's lower between H2SO4 and H2SO3 because it's less dissociation. But again, when we're talking strong acids, we're not necessarily talking about concentration. We're talking about the ability to dissociate. Okay? When we're talking about strong bases, your strong bases are your hydroxides or oxides. We call them pretend bases because what happens if you put a metal oxide in water, you get a metal hydroxide. So they are considered strong bases with the exception of magnesium and beryllium. Okay? Solubility also plays a role. If something is very, very soluble, then it tends to be a strong base. If something is mostly insoluble, it's not going to, since it's not dissociating, it makes sense that it would be weak. So here is the stronger the acid, the weaker the conjugate base, and vice versa. This is going to be an important concept, okay? So you might even want to jot this down. A strong acid is going to give you a weak conjugate base. A weak acid will give you a strong conjugate base, and vice versa. Strong base is going to give you a weak conjugate acid, and a weak base is going to give you a strong conjugate acid. I'm not sure what that noise is. Sorry. Okay, so strong give you weak, weak give you strong. Okay, that's the nutshell. So weak acids, the majority of acids and bases are weak. Okay, it means they don't ionize very much. This means equilibrium is established, and it lies far to the left because the reactants are going to be favored if there's not much dissociation. That makes sense, right? So here we have this weak acid in water, and what's going to be favored? So your K value is going to be less than 1. And so this is what the Ka value, and of course Ka means acid. Okay, so we would leave out water. Why? It's a liquid. It's a pure liquid. So you leave out water, so you get this equation right here. Ka is going to be equal to the hydronium times the concentration of your conjugate base over your weak acid. Okay? So that's what your Ka values today. So here are some common Ka values that you can look at. One that you will probably become very familiar with, whether you want to or not, is this one right here. They like to have acetic acid show up a lot. Acetic acid shows up probably the most commonly for weak acids in these problems, and ammonia shows up the most common in that, and both of them are 1.8 times 10 to the negative 5. They both have the same, like, it's funny. But those are values that will either be given to you or you can look up, or they may possibly ask you to solve for it. Okay?
If they ask you to solve for it, will it?
They'll give you concentrations.
Okay.
Yeah, kind of like KSP. If they ask you to solve for it, or K in the last unit, if they ask you to solve for it, they'll give you information. Now, it may not be right smack beat you in the head with it. You might have to get to it because of the information they give you, but there's always a way to get there. There is never an unsolvable problem on the AP exam or on any of the tests I give you. It's just you have to find out how to solve it.
And if you get like 1.5 it's 7.9, but you know it's 1.8.
No, you should go based on sig figs. Okay. So write the Ka expression for acetic acid. So leaving out the water because it's a pure liquid. So first of all, acetic acid is HC2H3O2. Also, make sure you recognize acetic acid is this as well. Both ways show up. The first way is the inorganic chemist way. The second way is the organic chemist way of writing it. So which one do you want me to dissociate? Okay.
Will it end up the same way?
Well, yeah.
I do the organic.
Okay. So Ka expression would just look like this. And it is perfectly acceptable to leave out the water when you're doing it this way. No, not H2. Whoopsies.
So the biological way, that's like the structure that it forms, right?
The organic chemist way?
Or organic chemistry, yeah.
Yes. So if I were to draw that structure out, it looks like this.
Right.
And then C, and then double bonded O, OH. So that's called a carboxylic acid, and it is something you should recognize in the structure. When you see this, the Ku part on the end of something, that's indicating that it's an organic acid.
Okay, so it's better to do organic.
It's not either. Either way is fine. Now you need to recognize both way,
Well, that's more information.
but if it's neither way is better. And in terms,
But in general, it's a
that's-
better way to
depends on if you're an inorganic chemist, they don't agree with that. And then this way, of course, would be the H plus, the CH3Cu, and the acetic acid on the bottom. Whoops. Sorry, I'm writing it back the other way. Okay? So we good? So far, so good? Haven't done anything too hard? Weak bases are bases without hydroxide. React with water. They react with water to produce a hydroxide. Most common example for us is going to be ammonia, methylamine, ethylamine. The lone pair on nitrogen forms a bond with hydrogen, and most of the weak acids are going to involve some nitrogen. Okay, the amine ones are going to stink. Amines smell bad. Yeah. Okay, so the equilibrium expression for bases is known as Kb, the B for base. Okay, so here we have our weak base reacting with water to form a conjugate acid and a hydroxide. So then our expression is going to be, leaving out the water, of course, the conjugate acid with the hydroxide over the weak base. And again, much, much less than 1, because just like in the acids, the reaction is favored towards the reactants. Here are some common values, and ammonia is the one that shows up, and its Kb value is 1.8 times 10 to the negative 5. I just think it's weird that the two most common are 1.8 times 10 to the negative 5, Ka and Kb. It's just kind of funny. Okay? All right. So write the Kb expression for ammonia. And luckily, there's only one way to write ammonia. Okay? Now, we're leaving out the water, but water is assumed to be there. So it would form what? Ammonium and hydroxide. The water is assumed. Okay, so you don't have to go back and try to balance it. The water is assumed. So our Kb would be NH4 plus times hydroxide concentration over the NH3, which is equal to 1.8 times 10 to the negative 5. Okay? Is everybody with me so far? Nothing too drastically hard? Okay. Obviously, the Ka and Kb look very similar. Another note, I don't know if y'all caught it, but these are interchangeable. The H plus and the hydronium are interchangeable. Okay. Both are acceptable. I will almost always use H plus. It takes less time to write. Okay? But if you like the hydronium and you want to write HCO3 plus, that's fine. Okay? Because we're assuming the water's not there. Not assuming that it's not there. We're assuming that the water is there so we don't show it. But you do need to be aware that these are all aqueous. Otherwise, there would be no dissociation whatsoever because there's nothing to dissociate in.
Can they dissociate in air?
Oh, nope, they cannot. So using the table, we're going to arrange these species according to their strength as bases. Okay? So remember I told you if it was from a base, to be a strong base, it needed to come from a weak acid. Okay? So we're going to start with the weakest base. So which one? I know the answers are on your paper, but try not to look at them. Which one of these would have come from the strongest acid? Chlorine. So it is going to be the weakest base. So it's going to be less than. Okay? But you use your Ka values or your Kb values. In this case, you're going to use your Ka values because you're wanting to see if it came from a weak acid or a strong acid.
Oh, we use the table?
Yeah, table 14.2. So what would be the next strongest? H2O, yep. I know that it's on their thing, but look at their, then after that. And if it helps, you can jot what acid it came from. If that helps you, this came from HF, this came from HCl, this came from HNO2, and that came from HCN. So that kind of might help you as you're looking through that table. So what comes after that? I think it's the fluorine. Then you got to look between NO2 and the CN. Which one is? So basically, which one is the weakest acid of all of those? The HCN is. So then this would be HNO2. And then, not HNO2, just the NO2, sorry. And then CN. Those would be the strength. So you got to look at weak makes strong, strong makes weak.
So is there like no way to know besides when you have a table?
If you don't have a table, no. If they're wanting you to do it without the table, they would probably include some, some strong and some weak and some water in there. Okay. Okay. All right. Water, the hydronium, and the auto-ionization of water. Water has this unique ability to auto-ionize itself. So really and truly, when you're drinking water, you're not drinking H2O, you're drinking hydronium and hydroxide ions in equal concentrations. Okay? Since it's amphoteric, it may, well, not so true. I'll just keep going. So that brings us to the equilibrium expression, which is Kw, which stands for the auto-ionization constant for water. And it is equal to 1 times 10 to the negative 14. So what that means for us is if we know the concentration of one of our ions, then we can figure out the concentration of the other. Because no matter what, the concentrations times each other is always equal to 1 times 10 to the negative 14. Okay? So if your hydrogen concentration is greater than your hydroxide, then you have an acidic solution. If your hydroxide is greater than your hydrogen, then you have a basic. And if they're even, Steven, equal, then you have a neutral solution. Okay? Does that make sense?
Yes.
Good, because it should. Okay? So at 60 degrees Celsius, which, by the way, the value is tied to temperature, at 60 degrees Celsius, the Kw is 1 times 10 to the negative 13. So, first of all, using Le Chatelier's principle, predict whether this reaction is exo or endothermic. I know the paper says what it is, but you have to tell me why. Why, pray tell? Well, what does the KW value tell you about it? It's really, 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 really small.
Yeah.
And when we have a KW value that's really, really small, and it got smaller, actually got larger at a higher temperature, right? Negative 13 is higher than negative 14, right? So it increased when we increased the temperature. So what does that say?
It's endothermic.
It's endothermic.
Because
We
energies
started
are
making,
reacting.
we started shifting. So the fact, when we heat something up, if it makes the forward reaction go higher, that was endothermic.
Because energy is a reactant.
Because energy is a reactant. So this is endothermic, which we already said down here, but that's the reason why. And then calculate the H and hydrogen, I can't talk. Calculate those concentrations. So remember we have KW is equal to this. It gave us the value of 1 times 10 to the negative 13 is equal to x times x, which is x squared. So to get each value, it would be the square root, of 1 times 10 to the negative 13. Simple math?
Quick maths.
Say what?
Quick maths.
Yeah. So when you take the square root of that, you get this number right here. Because once you know one, you can find out the other.
So, like, the only way to figure out whether it's exothermic or endothermic is if you have two of the values at different temperatures?
Yes, but you always have it at 25 degrees Celsius. That is a defined value. KW is 1 times 10 to the negative 14 at 25 degrees Celsius, which is considered standard conditions, not standard temperature, standard conditions. So when we're talking standard conditions, we're talking about 25 degrees Celsius. So unless they give you a temperature, you assume that it's standard conditions. So most of the time, they are going to assume you know that KW is equal to 1 times 10 to the negative 14.
But what if it's like, if it's not water, if it's like something else? And you have to tell
It's still in water.
What?
Any acid or base is still in water.
Okay.
So yes, this works for whatever acid and base you have because it's still aqueous. So no matter what solution you have for acids and bases, if you're at 25 degrees Celsius, your KW value is going to be 1 times 10 to the negative 14.
Okay.
Okay? Because even though we've got some stuff dissolved in there, we still have majority of water.
What about like on the past test or whatever, when it was like asking something that was endo or exothermic, or like just giving you a random reaction or something? Like, would you be able to tell?
When they're asked, well, this is still the same concept as in the last unit about the value going down. Right now, because I have still two people that haven't taken the test, I would prefer to discuss anything about the test either privately or after everybody's taken the test,
Okay.
because that would give them an unfair advantage.
None of us had an advantage.
Yeah, I had quite a few A's.
Well, most of us didn't have an advantage.
The only reason we can do that is because it's neutral, right?
Yes, because if you were, yeah, KW, well, no. What do you mean, what's neutral? Say that again. I don't think I understood the question.
It says the solution was neutral so that they were both X.
Yes, yeah. Now later on, it's not neutral. If you know one, you can get the other one, which we're going to do here in a second. What time is it? Actually, I think this would be a good time to stop because I won't be able to finish the pH scale, so let's stop here.